Hello everyone. Let's get back to the class 4, part 2, power system. Last video I talked about three-phase three-phase AC system and how delta Y connection and what is the relationship between line to line and phase voltage and current between delta and Y connections. Today we're going to talk about circuit analysis for three-phase systems. So if you have a delta or Y connection, if they're balanced, that means all the phase has the same amount of impedance. So that you can go back from delta to Y by using this equation over here. So Y connection for phase impedance could be delta connection for phase impedance divided by 3. So let's say we have a delta connection over here. See, Z delta is 100 plus J 36 ohms. If you go into the, what do you call it, polar form over here, that would be 106.28, 19.80 degree. Now, if you go into Y connected load, the impedance would be equivalent to ZY is Z delta over 3. That will give you, 33.33 plus J 12 ohms here, so ohms here. Then that would be equal to 35.42, angle is 19.8 degree ohms. So look at here. This one divided by 3 will give you this one here, but angle does not change. So we are not changing the angle, only the magnitude of the impedance will change if we go from delta to Y or Y to delta. So that is Y delta transformation for the load. Now, we're talking about balanced system. Balanced system means that all phase quantity are the same, right? Only difference is the angle. So, for example, if I have a generation over here, which is three-phase generation, right? Then let's say that is, I'm connecting that to a load that's also, let's say, yeah, I can convert it to delta or Y as I need them. So let's say that we have a delta connected load over here, so Y connected load over here, right? And each load, let's say, has a impedance of GP, right? And let's say each of these, now let's say this is my terminal A, this is my terminal B, this is my terminal C over here, right? Then all of these over here, let's say EB over here, EA, EC, right? EA, EB, EC, you all know that they have the same magnitude, but they're apart from each other by 120 degrees, right? And also load has the same magnitude, they're apart from each other by 120 degrees. And over here, this also has the same impedance over here, line impedance for everywhere here, right? So that means to analyze the circuit for three-phase balanced three-phase balanced system through circuit analysis, I don't have to do all three phase. If I can do one phase, and if I know voltage and current for that phase, other two phase can be just followed them by 120 degree from there, right? So that's why I can only take, let's say here, if I can take this one phase, let's say phase A, and let's say this is connected, virtually connected the neutral here. So I can take phase A out of here, right, with the neutral, and bring it over here and analyze that, find all the voltages, currents in this phase, that phase, then I can go back to other phase that would be 120 degree apart from this phase, right? So that's how it's called per phase analysis. That only can be done for the balanced system, right? This only can be done by the balanced system. Also, balanced system, you have to understand that if we add all the current, for a balanced system, there's no neutral current. That means all the current summation will give you the zero. All right. So here again, perfect analysis we can do for the balanced system, because balanced system their magnitude for each phase are equal to each other. Only difference is the phase. So if I know the magnitude for current voltage, then I can easily find the current voltage for other phases by just adding 120 degree to that phase. So let's put everything together here. If I have this circuit to solve, so how do you start here? How do you start here? How do you start to see that how to solve this problem? First of all, do not try to solve any circuit in delta load combination. So first thing first, you have to find equivalent circuit from delta to Y. So if I do that over here, that means I have to see, let me get my color change over here. So that is Y connection, right? So how do you go delta to Y? You divided delta impedance by 3 to get the Y impedance. So that means all of this would be now 6 ohm, right? So I can now redraw this over here. So redraw this here. That's all phase line has the same impedance. Then I also have this. So that is, this one is goes here, and this one goes here, and this one comes from here. All right, good. So these are all 12 ohm. That's neutral here. Now I made this one also a Y connection here, so I can draw this over here same as this one over here. So I can say that this one comes over here, this one comes over here, and this one comes over here, right? So now from here, if I undertake this is A, this is neutral here, this is neutral here, A, B, C. If I take the A to neutral out of here, so let's do that. If I take the A to neutral out of here, so there's J3 ohms here, and I have a 12 ohm from there to neutral here, right? Then I have another 6 ohms over here, is a conversion from delta to Y. So that is also a 6 ohm over here from there to neutral. So now look at that. So now my circuit from A to neutral came to that. So when I know the current here and voltage A to neutral, I can easily find others. So now I'm going to go to the next one here. So let's show you this here. So now A, so now I can make the combination of 6 and 12 over here. All right. So 6 and 12 will give you, if you combine 6 and 12 in parallel combination, you will get, let me see what I have over here. I should have that done over here. That should be 4 ohm, right? So my circuit became a very simple circuit here, right? So now your voltage, if I go back to this circuit over here, your voltage over here is 346.41. This is line to neutral. This is line to neutral voltage, right? I have to convert that to line to, so this is line to line voltage. I have to convert that to line to neutral over here. So line to VAB was given 346.41 volts. I need VAN. Remember that I have A to neutral, right? So I have to divide this one by, remember that there are root 3, square root 3 factorial there, remember that. So if I divide that, that becomes 200 volts, right? So I'm going to use that as my reference. I'm going to use this one as my reference voltage. So then my voltage over here, VAN, is 200. When I say reference, I'm going to use 0 degree angle there, right? Right. So now I can easily find the current here now. Let's say current IA. So the IA would be VAN, right? VAN over whatever the impedance there, right? So VAN over impedance is what? I have 4 plus J3, right? Right? So if I do that, my current would be 40, negative 36, 87 degree, right? So once you get the current over here, you can find all other quantities. Let's see. So now I know BAN. I can find BN, BCN. I know IA now. I can easily find IB, right? IB should be same magnitude and 120 degree, negative 120 degree from here. So 136, 120 would give you negative 156.87 degree. Now you should be able to find IC, right? That's what I'm saying. So now, if you want to go back to your three-phase analysis, now you say I want to find the current at let's say some other point, any other point you want. So you can easily do that too from this analysis. We're gonna finish this in the class. I'm just trying to give you some analysis here. So I already talked about this three-phase voltage and currents. As I say, the constant three-phase real power and also reactive power over here. So if you add them together, you get three-phase. You will get three-phase complex power. So S three-phase is P three-phase plus J Q three-phase. That also same as three-phase voltage times phase current conjugate. So that's the same here. Remember that your single phase, I'm gonna 1P over here, single phase, you have VI conjugate. Here for three phase, I have 3 is phase current, sorry, phase voltage is phase current and conjugate. So that is the three-phase complex power. We're gonna do a little bit more into that in next slide over here. So balanced three-phase power for Y-connected load, right? So here you have S, right? Three-phase current, phase voltage, cosine theta, right? So that is let's take this cosine theta out of here. So that is your conjugate over here. Let's conjugate over here, right? That is your complex power. That is your complex power. And what is your real power? It's all three phase. Remember that it's all three phase. Is 3 BP, IP, all phase quantity here, and cosine theta, right? Remember that for Y connected load, your line current is equal to phase current, right? So your line current is your phase current. And your line-to-line voltage is square root of 3 times your phase voltage, right? That's either magnitude difference out there. So now, what it means that your phase voltage is 1 over square root of 3 times line to line, right? So if I now convert this equation over here with this quantity here, so phi three phase would be 3 times 1 over square root of 3 line to line voltage times line current cosine theta. Remember that line to line, line to neutral conversion does not change the phase angle. All right. So if I now put it together here, it would be square root of 3, we're gonna have square root of 3 left here. We line to line, I line voltage cosine theta. Right. I can do the same thing for reactive power. It's also the same thing. So it will be sine theta, right? Now, if I come to the delta connected load, for delta connected load, you know that your IL is square root of 3 times IP, right? But your line to line voltage is equal to your phase voltage, right? So if I now modify this one here, it will be same. If you do the math over here, you will see the same thing. And it also get the same equation here. So what does it mean? It means that doesn't matter what kind of connection you have, your power equation does not change. So, so this is the most commonly used power connection here. If you know the line-to-line voltage and line current, and one thing is that in three-phase system, your problems always give you line-to-line voltage and always give you line current. They would never give you phase current and phase voltage. Whatever voltage is given is always line to line. It's always line current. All right. So remember that. Again, we actually we'll finish this in the class. All right. So you also finish this one in the class. All right. I think we are almost end of the chapter here. So here's the thing. You have two different connections, delta connection and Y connection. Whatever connection you have, always for the solution, to solve problem, delta needs to be broken down to Y. Then take one phase to neutral out. Do all the calculation. Do all the calculations. Then you can find other values from there. Like if you know one phase value, you can easily find the other two phases from there. So now to find the power and other things, let's say you need to find, let's say you know AN, right? Then you know IA, right? So to find the three-phase power, and also you know the angle between them. So for three-phase power, let's say real power over here, you can do 3 times VAN IA cosine theta. Then for reactive power, you can also do same everything here, sine theta. So is 3 is for the three phase. You're doing these are all the phase quantity here, right? So you're multiplying by 3 out there to do that. Or if you wanna go into line to line things here, so so line to line voltage is square root of 3 times line to phase voltage, right? So you can also find three phase over here with this equation here. Now you know line to line, and in delta connection you solve the problem in delta connection. Your line current and phase current are same, right? Then you have cosine theta. Then this one here would be same sine theta. Can you see that? It's basically same thing what you're doing. There's no difference. All right. That's all for today. I'll see you all for lecture 5 video.